Farmer discovered his horse was extraordinarily intelligent. You could ask it an arithmetic problem and it would tap out the answer with a hoof. Researchers were fascinated and tested the horse. They discovered the horse understood algebra, Euclidean geometry, calculus, and even group theory. However, when they gave the horse problems with Cartesian coordinates, it just stood there dumbly, like any horse. This was quite surprising, given how intelligent the horse was otherwise. They brought in an expert who examined the situation and explained the problem. Of course, the horse cannot understand any Cartesian coordinates. You show it. You were putting Descartes before the horse. And if you were older, you might have heard that phrase, putting the cart before the horse. And today we are doing scatterplots and correlation. Now, we did do the Barbie bungee jump activity. And what variables did we record in that activity to create our rubber band bungee cord? Now, we were kind of doing it more virtually, and we wanted to know things like number of rubber bands used and the distance traveled. Are those variables categorical or quantitative? They are quantitative. So when we have two different variables, so it wasn't just one we were recording, it was two. And we expect there to be a relationship between those two. In fact, one of them can be used to predict the other. So the explanatory variables, that would be the number of rubber bands used, are used to predict, and they're the input. And the response variables record the outcomes, what you're trying to measure. So as I mentioned before, the number of rubber bands we use explains how far the Barbie travels. One thing you do need to do when we create these scatter plots for relationships is to describe them. And we describe them using direction, unusual features, form, and strength. All right. If you've ever been a Homer Simpson fan, maybe one way to remember this acronym is DUFS. You remember Homer's favorite beverage? So direction, unusual features, form, and strength. The dots are either increasing, decreasing, or kind of staying constant with no pattern, usually, as you move left to right on the plot. This can be used to describe the relationship between the variables as having a positive correlation, or I should say, correlation, a negative or zero association. So you can see here, this is positive, this is negative, and this is not really much of any correlation, all right, or association. We can say association and correlation. The one we have to be careful about is the causation. All right, so this graph here is a scatter plot of distance for one of our data that if we use centimeters and number of rubber bands, okay? So unusual features, how do we check that? Are there any outliers or other unusual features? Don't really have any here, so no unusual features. And then form is either linear, non-linear, so you can see this is sort of curvy. This is pretty linear, or really no form whatsoever, just sort of a scatter. Strength tells us how strong that linear relationship is. We usually say strong or weak. So we would say this one is strong and this one is weak. For this graph right here, see, I noted that the form was linear, the strength would be strong. Okay, so one group missed the Desmos activity and collected data later using their own Barbie, all right? And they measured the number of rubber bands and the distances in inches. We're going to go ahead and try to measure the strength of the fit, how linear it is. So first things we're going to do, just like we're doing in all other statistics, is we're going to calculate the averages for the number of rubber bands and the distance. So the average number of rubber bands was 3.5 for this set of data. And the standard deviation, like I just throw that in a list and calculate it maybe on Stacklet, is 2.449 bands, all right? And then I throw in the distance, and what is the average distance here? Well, I add these all up, divide by 8, and I get 20.25 inches. So on average, the Barbie went 20.25 inches. And there's the standard deviation, 6.112 inches. Okay. So we're going to use this later because I'm going to show you how this comes into play. We're going to actually look at the deviation from the averages for the x and for the y. So on your table, I've already filled it out for most of the values. You're welcome. So we have x minus x bar. X bar is 3.5. All right. So how would we do that? That would be 6 minus 3.5. And then also I need y bar too, which is 20.25. So 6 minus 3.5 is 2.5. 26 minus 20.25 is 5.75. When I multiply these two together, I get 14.375. And I do the same again for the 7 rubber band data, 7 and 30. And we get 34.125. So our average is kind of like in here. And you can see that the deviation tends to be negative before the average, right? For both x and y. And it's positive after the averages for both x and y. And if we look at the products here, are there any negatives? No, they're always positives. So we're going to describe the graph, and I did this using a Staplet, and you'll see how you can put your data in Staplet on there. I also have some extra note handouts for that, or video. How would we describe the direction of this? Definitely positive, because it's going up from left to right. Is the product x minus x bar and y minus y bar usually positive or negative? So if you saw on the table, you saw it was always positive, all right? So here's how we're going to look at it in a different way. I'm going to go ahead and mark this point x for the x bar, y bar. So the average x was 3.5 rubber bands, and the average y was just over 20 inches. So let's go ahead and mark that spot. So that's where my average is, all right? Well, if you look at when x is above average, then it looks like y tends to be above average, right? So the product is always positive here. And that's because positive times positive is positive. If I look when it's below average, well, then these values are going to be negative times negative. And when I multiply them, I also get positive. The form is definitely linear, and that's the only kind of regression we are going to do in our statistics class. And the strength is strong. Why is it strong? There looks to be a pretty linear relationship right there. Now, you can actually calculate correlation. This is the formula. Now we have n minus 2. This has something to do with degrees of freedom. And you take the deviation from the x average and the deviation from the y average. You take those products and you divide by the standard deviation. So we can actually calculate R. All right, I'm not going to make you do it that way, but you can. All right, so what does this remind you of? It looks like variance, except we have these extra values here where we're kind of standardizing it to the standard deviation of our sample. So when we're trying to do correlation, what we're trying to do is figure out which line would fit the best. Now, I'm actually showing you something called a residual. So if one thing I could do, let's say I had all these values and I wanted to predict what the average y value was. Well, I could just actually use the average y value, which is represented in this point right here. In fact, if I adjust this, you can see the average value changes. So this point represents the coordinates for the average x and the average y. But you're probably thinking, oh, you could do better than that, because if if x is high in this case, y is low, I should be predicting below the average value. If x is low in this case, y is high. So let's go ahead and do this. I'm going to adjust this line until I make these residuals hopefully as small as possible. This seems more like the line I would want. Now, I do have a way of turning on the actual regression line, and I'm pretty darn close to it. And you can see that this is a very negative regression, all right? This is called the correlation, which is R, and it measures the strength of the correlation. In this case, if I were to put these points, let's go ahead and line them up all on a line the best we can. I'll just move them to my line that said move this. All right, so I'm just trying to put all my points on that line the best I can. Here I got -1. Now that doesn't mean that the slope is -1. What it means is that it's perfectly correlated or almost perfectly, there we go, so that if I go down one certain way in x, then I go down the same way in y. That's, again, not to confuse it with the slope, because the slope here is negative 0.4. And that would say for every increase of 1 unit in x, I would go down negative 0.4 in y. What this correlation means is, think of it almost like a percentage, although it's not quite. It means that we are, all our change is explained by this line. Now, can you have positive correlation? Sure. So let's go ahead and adjust these. And what is this biggest value of ours? Well, you'll notice I'm kind of messing with the dots now. And if I look at it, my R is getting very low. So how strong is this equation here, or this linear form? It's not very strong. In fact, if I make a nice little circle with the whole thing, like I just sort of have some dots around, it gets pretty darn close to 0. So the closer this is to 0, the weaker the strength. All right, now we're going to go ahead and make this some more of a positive correlation. So it doesn't matter which points you have where. And I'm going to try and make this perfect. So tell you what, I'm going to try and line up. Come on. I'm going to try and line up perfectly here. So this C is going to get on my line. And this A is going to get down on my line. And that's pretty close. Come on, B. There you are. All right. Oh, the strongest I could make this, and here, let me move the equation so you can see it, is a value of 1. So strongest correlations, and I'm going to go ahead and do this again with a steeper slope. So my slope is, not worried about that label, trying to get everything beautiful. And you can see that, again, I have a different slope this time, 0.72, and my correlation is still 1. So the correlation is just how well the x value predicts the y value. It is not the same as the slope. And we do have some ranges that we can use to determine the strength of the correlation. So we do have some guidelines. So this form and the strength for the largest possible value of R, well, R was 1. That was the biggest we could make it. And that was very linear with a strong positive association. When we had the most negative value of R of negative 1, it was still very linear, but there was a strong negative association. Is R the same as the slope? No, R just measures strength. Slope measures how much y changes with 1 unit change in x. And remember, when you're interpreting slope, I expect you to tell me how much whatever it is we're measuring for the response, the y variable, changes with every increase of 1 in the explanatory or x variable. So here we go. The possible values for the slope, we noticed when we had a negative slope, correlation was negative. When we had a positive correlation, our slope was positive. So the signs on correlation and slope should always match. The strength, the most strongest ones we were at negative 1 and 1. So this is one rough guideline. From negative 0.8 to negative 1 is considered strong. From 0.8 to 1 is considered strong as well. The weakest correlation we had was at 0, which was right here in the middle. And then again, we'll have these two are moderate. So they're in between the weak and the strong. Now, let's go ahead and match these images with the values of R. Negative 0.928. That means we have a negative slope, and since it's very close to negative 1, it's a strong correlation. Which one of these looks the strongest? I would say that one right there. And it has a negative slope. This one is also a negative slope, and this is the only other one, so I know automatically it's this one. Notice how the correlation is in the weak area. It's between negative 0.5 and 0, so I would say that's the correlation for that graph. Then 0.002 would be very weak for linear. While there's a very strong association and pattern here, as far as doing a straight line, it's very weak. So we would say that's 0.002. And finally, that leaves us with 0.711, which is a positive, so we need a positive slope. And it's a moderately strong correlation. It's in between these two right here. So let's go ahead and look at one group who was late, and they gathered their own data for the Barbie bungee jump. So here are their values, all right? And I went ahead and entered the data here using a Scatterplot, which is a very easy to use applet. And the question is, how safe do we feel with Barbie's bungee jump if we would use this data? So let's go ahead and look at the graph that they did. Finishing entering the data. And then we're going to click Begin Analysis when it's done. So here we go. And you can see right below it, there's one thing called Calculate Correlation. So we can see that there's a very strong positive association between the number of rubber bands and the distance. And it shows because the correlation is 0.992. So this is positive and strong. Now, one of the group members snuck some extra rubber bands to collect some more data because he wanted to win the prize. And he added this point in. How does this affect our correlation? Well, basically what that means is that it follows along the line. So it's going to give us an even stronger line. And our correlation does actually go up. It goes up to 0.998. Then one group member also recorded data, except he accidentally left off a digit, and he said 6 rubber bands and 6 inches. Well, we know that doesn't make sense because it's shorter than the Barbie. So how does this affect the new correlation? Well, because it comes off the line, it makes it weaker. In fact, our correlation drops to 0.838. Still strong, even with this outlier, which would be an unusual feature. Now, the group had not followed directions. You probably noticed those measurements were different from yours, and that's because they did it in inches instead of centimeters. So what do we do here? Convert all these to centimeters. And I went ahead and used Scatterplot to get my new data, and we'll see what R is for that. Should it really change, though? Because all I'm doing is changing scale of distance. I'm not really increasing any distance, just the units of measure. And let's see what happens to the correlation. Takes a little longer to enter the decimals. And begin analysis, calculate correlation, and what do we get? 0.993, which is very similar. There's probably some rounding issues because we converted